Look up at the night sky. What do you see? A scattering of stars, distant galaxies, perhaps a planet or two. But beneath this breathtaking view lies an invisible force, a hidden hand shaping everything from the smallest particles to the grandest cosmic structures. What if I told you that the universe isn't just held together by gravity alone, that there's another power, silent yet relentless, weaving its influence through the fabric of space itself? We're talking about magnetic fields, the cosmic architects working behind the scenes, sculpting the universe in ways you've probably never imagined. Think of them as the universe's silent puppeteers. Without them, stars wouldn't ignite, galaxies wouldn't spiral, and even the gentle dance of auroras on Earth wouldn't exist. Magnetic fields are everywhere, stretching across light years, threading through nebulas, and even humming deep within our own planet. They're the invisible highways guiding charged particles, the unseen shields protecting worlds, and the mysterious sculptors of cosmic landscapes. And yet, for something so fundamental, they often slip under the radar, overshadowed by more familiar forces like gravity. But today, we're putting them front and center. So grab your cosmic detective hat, because we're about to uncover 30 mind-blowing ways magnetic fields shape the cosmos. From the violent birth of stars to the colossal collisions of galaxies, from the secrets of black holes to the delicate balance that makes life possible, these magnetic mysteries are about to rewrite how you see the universe. And here's the wildest part: you're already standing in the middle of this grand magnetic story. Every time you've marveled at the northern lights, every time you've used a compass, you've brushed up against the very same forces that govern the fate of galaxies. So let's dive in, because once you see the universe through the lens of magnetism, you'll never look at the night sky the same way again. Picture a vast, swirling cloud of gas and dust in deep space, a cosmic cradle where stars are born. But without magnetic fields, this process would descend into utter chaos. As gravity pulls these gas clouds inward, they should fragment wildly, creating a messy burst of small, unstable stars instead of the majestic suns we see. So how does nature avoid this cosmic traffic jam? Enter magnetism, the unseen force acting like a celestial traffic cop, keeping everything in line. These magnetic fields thread through the gas clouds like invisible wires, channeling the collapsing material into orderly streams. Think of it like water spiraling down a drain, but instead of random splashes, the flow follows an organized path. This phenomenon, called magnetic braking, slows down the spinning gas just enough to prevent it from tearing itself apart. Without this delicate balance, star formation would be a cluttered mess, and the universe would look entirely different. The proof is written across the night sky. Take the Orion Nebula, one of the most stunning stellar nurseries visible from Earth. Those glowing filaments and twisted tendrils of gas, they're shaped by magnetic forces, sculpting the raw material of stars into intricate patterns. Like cosmic architects, these fields compress gas into dense knots where gravity can finally take over, igniting the fires of newborn stars. And here's the wild part: magnetic fields don't just guide star formation, they also dictate a star's future. The strength and alignment of these fields determine how fast a star will spin, whether it will develop planets, and even how long it will live. So next time you gaze at the stars, remember, every one of them owes its existence to the silent, guiding hand of magnetism. The sun might look calm from here, but make no mistake, it's a seething ball of plasma, twisted and tangled by magnetic forces beyond our imagination. And when those magnetic field lines get wound too tight, they snap like an overstretched rubber band, unleashing one of the most violent events in our solar system, a solar flare. In just minutes, these explosions release energy equivalent to billions of hydrogen bombs, launching superheated particles across space at nearly the speed of light. But here's where it gets personal. Those eruptions don't just vanish into the void. They barrel straight toward Earth, crashing into our planet's magnetic shield like a cosmic tsunami. When they collide, the results are both breathtaking and disruptive. On the beautiful side, we get the auroras, those shimmering curtains of green and pink light dancing across polar skies. That's solar particles spiraling down Earth's magnetic field lines, striking our atmosphere and setting the night aglow. Yet there's a darker side to this celestial light show. A powerful solar storm can fry satellites, knock out power grids, and even disrupt GPS signals. Picture this: in 1989, a geomagnetic storm left 6 million people in Quebec without electricity for 9 hours, all because of tangled magnetic fields on the sun. And the most intense solar storm ever recorded, the Carrington event of 1859, set telegraph wires on fire and produced auroras so bright people could read newspapers by their glow at midnight. Today, with our reliance on technology, a storm of that magnitude could plunge entire continents into chaos. That's why scientists constantly monitor the sun's magnetic activity, watching for those telltale signs of brewing storms. Because in the grand cosmic ballet, Earth isn't just a spectator, we're part of the dance, pulled and pushed by magnetic forces that stretch all the way from the sun's fiery surface to the edges of our atmosphere. Ever wondered why galaxies like our Milky Way have those beautiful, sweeping spiral arms instead of collapsing into shapeless blobs? The answer lies not just in gravity's pull, but in the invisible scaffold of magnetic fields holding it all together. Here's the cosmic secret: those elegant galactic arms we see in telescope images aren't just chains of stars. They're actually reinforced by vast magnetic filaments, like steel rods woven through concrete, giving the galaxy its structure and preventing it from dissolving into chaos. Scientists discovered this by running computer simulations, one set with magnetic fields, one without. The results were staggering. Without magnetism, galaxies turned into formless puddles of stars, their spiral arms melting away like butter in a hot pan. But introduce magnetic forces, and suddenly those same galaxies developed crisp, defined arms that matched what we observe across the universe. That's because these fields act like cosmic guide wires, channeling gas and dust into orderly lanes where gravity can then shape them into those iconic spirals. Radio telescopes have now captured stunning proof. Images from facilities like the Very Large Array reveal ghostly magnetic threads perfectly aligned with the Milky Way's spiral arms. Think of them as celestial train tracks directing the flow of cosmic material. Some of these magnetic filaments stretch for thousands of light years, stronger than anyone predicted. They don't just passively trace the galaxy's shape, they actively maintain it, resisting forces that would otherwise blur those spiral arms into oblivion over cosmic time. What's truly mind-blowing is how these magnetic structures self-reinforce. As stars form along the spiral arms, their stellar winds and supernova explosions pump energy back into the magnetic fields, creating a feedback loop that preserves the galaxy's architecture for billions of years. It's nature's perfect balancing act where gravity builds the spiral and magnetism keeps it sharp. So when you next see an image of a spiral galaxy, remember, you're not just looking at stars. You're witnessing the grand collaboration between gravity's pull and magnetism's invisible hand, a partnership written across the fabric of the cosmos itself. Deep in the heart of supernova explosions and around the churning edges of black holes, nature operates its own particle accelerator, far more powerful than anything we've built on Earth. These cosmic speed traps don't use magnets in a lab. They rely on shock waves racing through twisted magnetic fields, turning space itself into a slingshot for subatomic particles. When a star explodes, the blast wave doesn't just dissipate, it rips through surrounding magnetic fields like a tidal wave, stretching and compressing them into chaotic knots. Charged particles caught in this turmoil don't just drift, they get whipped back and forth across the shock front, gaining a sliver of energy with each pass. Over hundreds or thousands of crossings, what began as a slow-moving proton ends up hurtling through space at 99% the speed of light. That's how cosmic rays, the universe's most energetic particles, are born. But these aren't just space oddities, they're elemental alchemists. When ultra-fast cosmic rays smash into slower atoms drifting between stars, the collisions forge rare elements like lithium, beryllium, and boron, ingredients you won't find cooked up in ordinary stars. Every time you check the time on a lithium battery or hold a beryllium alloy golf club, you're handling stardust forged by magnetic mayhem. Yet there's a darker side to this interstellar speedway. A single high-energy cosmic ray carries the punch of a major league fastball packed into a particle smaller than an atom. For astronauts outside Earth's protective magnetic bubble, that's a serious hazard. During solar quiet periods, cosmic rays can pierce spacecraft walls, zipping through human tissue like microscopic bullets. Scientists tracking astronauts' brains found these particles leave tiny trails of damage, potentially affecting cognition on long missions to Mars. Even air travelers aren't completely safe. A transatlantic flight exposes you to as much radiation as a chest X-ray, all thanks to cosmic rays funneled toward Earth by our planet's own magnetic field. So while these magnetic particle cannons paint our skies with rare elements, they also remind us that space isn't empty. It's a shooting gallery of invisible bullets, each one a testament to the raw power of magnetism in the cosmos. Take the most powerful magnet you've ever seen now, crank its strength up 100 trillion times, and you'll start to approach the unimaginable forces surrounding neutron stars. These cosmic remnants, born from supernova explosions, pack more mass than our sun into a city-sized sphere, spinning faster than a blender blade, but it's their magnetic fields that truly defy comprehension. While Earth's magnetic field might gently nudge a compass needle, the field around a neutron star is so strong, it doesn't just influence matter. It violently rearranges it at the atomic level. Picture a single teaspoon of material from a neutron star's surface. On Earth, it would weigh billions of tons, but under these magnetic forces, it wouldn't even stay three-dimensional. Atoms get stretched into needle-thin strings, their electrons torn away and forced to move in perfect spirals along the magnetic field lines. The result: matter flattened into two-dimensional pancake structures that simply couldn't exist anywhere else in the universe. Then there are magnetars, the neutron stars that take this magnetism to apocalyptic extremes. When their crusts crack under magnetic stress, they unleash starquakes so powerful they ripple space-time itself. In 1/10,000th of a second, a single quake can release more energy than our sun emits in 100,000 years. These convulsions twist magnetic fields into knots tighter than any sailor could fathom, generating bursts of gamma rays detectable across the galaxy. But perhaps the strangest effect lies in how these fields warp reality itself. Light passing near a magnetar doesn't just bend slightly, it gets violently twisted. Photons split into two separate beams like light through a crystal, a phenomenon called vacuum birefringence predicted by quantum theory, but only observable near these cosmic monsters. Even the vacuum of space ceases to be empty here, with magnetic forces so intense they shake virtual particles into existence. These stellar powerhouses serve as natural laboratories for physics we can't recreate on Earth, where magnetic forces overwhelm even gravity and the very rules of matter get rewritten. Every time astronomers detect a flicker from one of these distant beasts, it's a reminder: the universe holds forces far stranger than anything we experience in our quiet corner of the cosmos. Earth's magnetic field isn't just an invisible curiosity, it's a planetary force field, standing guard against the relentless assault of charged particles streaming from the sun. Picture a vast teardrop-shaped bubble surrounding our planet, stretching over 30,000 miles into space on the sunward side and tapering into a million-mile tail behind us. This magnetosphere acts like a cosmic umbrella, deflecting the solar wind's deadly barrage of protons and electrons that would otherwise strip away our atmosphere molecule by molecule. The proof of its power lies just 40 million miles away on Mars, a planet that once had flowing rivers but now stands as a cautionary tale of what happens when that shield fails. Scientists believe Mars once boasted a global magnetic field and a thick atmosphere capable of sustaining liquid water. Ancient riverbeds and lakebeds etched across its surface tell the story of a world that wasn't always the frozen desert we see today. But when Mars' internal dynamo, the churning liquid metal core that generates magnetic fields, shut down roughly 4 billion years ago, the consequences were catastrophic. Without that protective bubble, the solar wind systematically dismantled the Martian atmosphere. Over eons, the pressure dropped to less than 1% of Earth's, allowing water to evaporate into space. Today, Mars' remaining atmosphere is so thin that liquid water instantly boils away even at freezing temperatures. The difference between our two worlds comes down to geology in motion. Earth's magnetic shield stays strong because our planet's heart still beats with molten iron swirling around a solid inner core. This planetary-scale generator creates electric currents that produce our global magnetic field, a process called the geodynamo. When solar particles encounter this field, most get funneled harmlessly around Earth toward the magnetic poles, where they create auroras instead of atmospheric havoc. Some particles do slip through, but at a rate our planet can easily replenish. Satellites like NASA's Maven orbiter have witnessed the solar wind's atmospheric stripping in action at Mars, measuring the eerie glow of oxygen atoms being ripped away into space. Meanwhile, Earth's continuous magnetic protection has allowed our atmosphere to persist for billions of years, maintaining the exact conditions needed for oceans to stay liquid and life to flourish. It's an invisible gift we rarely consider, yet this magnetic bubble may be the single greatest reason you're here to enjoy a breath of air today. Far out in the cold depths of interstellar space, where temperatures hover just above absolute zero, something extraordinary happens. In the darkness, molecules begin to dance. Not randomly, but in perfect unison, all pointing the same direction like iron filings near a magnet. These cosmic choreographers aren't visible to the naked eye, but radio telescopes have revealed their secret: vast clouds of gas and dust, threaded with magnetic fields that align molecules like tiny compass needles in the void. Here's why this matters. These dark molecular clouds are the universe's chemistry labs, where simple atoms link up to form complex organic compounds. But without magnetic fields, those reactions would be hopelessly inefficient molecules bumping together at random, rarely forming anything more elaborate than carbon monoxide. Magnetism changes the game. By forcing molecules to orient in specific ways, these fields act like cosmic matchmakers, dramatically increasing the odds that atoms will bond in just the right configurations to create life's building blocks. The ALMA telescope in Chile has captured stunning proof. In the twisting tendrils of the Taurus molecular cloud, astronomers detected methanol molecules, a key precursor to amino acids, all perfectly aligned by magnetic forces. It's like finding a factory assembling Lego pieces instead of scattered bricks, with invisible hands slotting each chemical component into place. These methanol molecules don't just float aimlessly. They spin in sync along magnetic field lines, their orientation so precise that they emit telltale radio waves detectable across light years. But the real magic happens when these magnetically guided reactions produce something called chiral molecules, compounds that come in mirror image versions like left and right hands. On Earth, life overwhelmingly uses one version: left-handed amino acids and right-handed sugars. For decades, scientists wondered how this preference began. The answer might lie in starlight passing through these magnetically aligned clouds. As polarized light interacts with oriented molecules, it can favor one chiral form over another, potentially seeding the asymmetry found in all living things. This cosmic chemistry doesn't stay trapped in space. When new stars and planets form from these magnetized clouds, they inherit these pre-assembled organic ingredients. Comets and asteroids later deliver them to young worlds like early Earth, raining down the very compounds that could jumpstart life. So the next time you look up at the night sky, remember, those dark patches between stars aren't empty. They're immense reactors where magnetic fields quietly assemble the pieces of life itself, one aligned molecule at a time. At the heart of some galaxies, black holes don't just devour matter, they spit it back out in narrow, high-speed beams that stretch for thousands of light years. These aren't random sprays of particles, but precision-engineered jets focused tighter than any laser we've built on Earth, the secret to their needle-thin precision. Magnetic fields acting like cosmic nozzles, squeezing turbulent plasma into disciplined streams. The iconic jet erupting from galaxy M87, the first black hole ever imaged directly, shows this phenomenon in stunning detail. Despite the chaos near the black hole's event horizon, its jet remains remarkably straight for 5,000 light-years, defying the expectation that such energetic outflows should fan out wildly. Compare this to computer simulations where researchers turn off magnetic fields. Without those invisible guides, accretion disks produce pathetic sputters, particles ejected in all directions like water from a hose with no nozzle. The difference is night and day. Real black holes don't have mechanical parts to collimate their jets. They rely on magnetic fields springing from the disk's ionized gas. As matter spirals inward at near light speed, it drags magnetic field lines with it, twisting them into a tight helix around the black hole's spin axis. This creates a natural particle accelerator. Charged material gets funneled along these corkscrewing field lines, while the field's own tension acts like a rubber band, keeping the jet from spreading outward. The numbers behind this process are staggering. The magnetic nozzle around M87's black hole channels plasma moving at 99.9% light speed, with energies a trillion times brighter than our Sun. Yet the jet's width remains astonishingly constant, only a few light-years across despite traveling interstellar distances. It's like threading a needle from New York to Los Angeles without missing the hole. Even more fascinating is how these magnetic structures self-correct. When turbulence threatens to disrupt the jet, kinks develop in the magnetic field that actually radiate energy away, allowing the flow to stabilize itself. Astronomers have spotted these magnetic reconnection events in real time, mini explosions along the jet that act like pressure release valves, maintaining its incredible focus. What we're witnessing is nature's version of extreme engineering, where magnetic fields transform chaos into order on a galactic scale. These jets don't just dazzle astronomers, they shape entire galaxies by heating surrounding gas, shutting down star formation, and even influencing how galaxies cluster together. So while black holes may be famous for their darkness, it's actually the magnetic brilliance around them that leaves the most visible mark on the cosmos. Stretching between galaxies like glowing threads in a cosmic spiderweb, vast filaments of hot gas weave the universe's largest structures together, and running through them, invisible highways of magnetic energy. These aren't just passive trails, they're dynamic power lines, ferrying enough energy to reshape entire galaxy clusters over cosmic time. Imagine the universe's matter distribution as a colossal three-dimensional map, where galaxies cluster along intersecting lines like pearls on a string. Now picture magnetic fields superimposed on that map, not random scribbles, but disciplined streams aligning perfectly with those filaments, as if someone drew them with a ruler. Recent observations from radio telescopes reveal just how integral these fields are to the cosmic web. When astronomers mapped the distribution of galaxies in the Sloan Digital Sky Survey, they noticed something peculiar about the spaces between clusters. Far from being empty, these regions shimmer with faint synchrotron radiation, telltale light emitted when electrons spiral along magnetic field lines. It's evidence of magnetic energy humming through the filaments, strong enough to influence the motion of ionized gas across millions of light-years. Here's where it gets truly wild. These fields don't just trace the cosmic web, they actively shape its evolution. Supercomputer simulations show that when magnetic fields are included, gas flows more efficiently along filaments, feeding growing galaxy clusters like water through a network of pipes. Without them, the gas would stall and disperse, leaving galaxies starved of the material needed to form new stars. The fields act as cosmic stabilizers, preventing turbulence from disrupting these delicate intergalactic supply chains. But perhaps their most dramatic role comes during collisions, when galaxy clusters smash together in some of the most violent events since the Big Bang. During these cosmic pile-ups, magnetic filaments get stretched like taffy, building up tension until they snap, releasing waves of energy that heat the surrounding gas to millions of degrees. X-ray telescopes have spotted these shockwaves rippling through clusters, their patterns matching exactly where simulations predict magnetic reconnection should occur. What emerges is a universe far more connected than we ever realized. Those same magnetic forces that guide star formation and sculpt nebulae also operate on scales so vast they dictate where and how galaxies gather. From the tiniest particle accelerators near neutron stars to these billion light-year conduits of power, magnetism proves itself not just a player in cosmic evolution, but the silent architect holding the universe's grand design together. Imagine standing on a gas giant 10 times larger than Earth, looking up as the sky explodes in colors so intense they'd cast shadows on the ground. This isn't science fiction, it's the daily reality on planets like Jupiter, where auroras don't just shimmer, they roar. While Earth's northern lights might paint delicate ribbons across the sky, Jupiter's auroras are continent-sized infernos, blazing with ultraviolet fury and pumping out enough energy to briefly outshine the sun itself. The secret behind this celestial light show, a magnetic handshake between planet and moon, so powerful it could power human civilization for centuries. Jupiter's magnetosphere is a monster stretching over 4 million miles toward the sun and tapering into a magnetic tail that reaches Saturn's orbit. But what really cranks up the auroras isn't just size, it's Jupiter's relationship with its volcanic moon Io. As Io spews sulfur dioxide into space at 1 ton per second, these particles get ionized and caught in Jupiter's magnetic grip. The planet's rapid rotation, spinning once every 10 hours, whips this charged soup into a frenzy, accelerating particles along magnetic field lines until they slam into the upper atmosphere at speeds approaching 5,000 miles per second. The result, auroras that aren't just brighter than Earth's, they're fundamentally different. While our auroras glow mostly green from oxygen atoms, Jupiter's blaze pink and purple from hydrogen emissions, with secondary rings dancing around the poles where magnetic anomalies focus the particle bombardment. Now picture a planet untethered from any star, a rogue world drifting through the interstellar void. You might think these nomads would be dark and aurora-less, but magnetism has other plans. Even without a solar wind to ignite them, rogue planets could generate ghostly auroras from their own internal dynamics. Subsurface oceans kept liquid by tidal forces might churn against a metallic core, sustaining a magnetic dynamo. Cosmic rays, those high-energy particles racing through the galaxy, could interact with these orphaned magnetic fields, sparking eerie, global auroras with no sunlight to compete against. The coldest, loneliest planet in the universe might still host silent light shows visible only in ultraviolet, a private spectacle for no one, the most tantalizing possibility. Auroras on rogue planets might actually help us find them. Current telescopes struggle to spot these starless worlds directly, but future instruments tuned to specific ultraviolet signatures could detect their magnetic whispers across light years. Every flicker in the dark could reveal another nomad, its atmosphere crackling with invisible energy, proof that even in the deepest isolation, the universe still finds ways to paint the skies. Before our solar system had planets, it was just a swirling disk of dust and gas, a protoplanetary pancake spinning around a baby sun. but hidden in that chaos was an invisible sculptor, magnetic fields threading through the disk like cosmic spider silk. These fields didn't just passively observe the construction of worlds, they actively directed the traffic, determining where rocky planets like Earth would form versus the gas giants further out. The proof is locked inside meteorites that have fallen to Earth, ancient time capsules from the solar system's infancy. Slice open an iron-rich meteorite under a microscope, and you'll find something astonishing: the magnetic orientation of microscopic metal grains frozen in place over 4.5 billion years ago. These tiny compass needles tell us the original magnetic field strength was surprisingly powerful, about as strong as a modern refrigerator magnet, but stretched across the entire protoplanetary disk. That might not sound like much, but across millions of miles of space, it was enough to orchestrate planet formation. Here's how it worked. As dust particles collided and stuck together, those with even a hint of magnetic material, like iron or nickel, began aligning with the disk's magnetic field like iron filings near a magnet. This alignment made collisions more orderly, allowing pebbles to grow into boulders, then planetesimals, and eventually planets. Without this process, dust might have just bounced around aimlessly, never accumulating enough to build worlds. The fields also acted like cosmic traffic lanes, creating zones where certain materials concentrated. Iron-rich particles migrated inward, explaining why Mercury ended up with a massive metal core, while lighter silicates dominated the outer disk, leading to gas giants with rocky hearts. But magnetism's role didn't stop there. Those same fields generated turbulence in the disk, not chaotic, but structured eddies that prevented newborn planets from spiraling into the sun. Scientists call this magnetorotational instability, and it's the reason we have stable orbits instead of a planetary pile up near our star. The math shows that without magnetic turbulence, all planets would have drifted sunward within 1 million years, leaving our solar system barren. Perhaps the most jaw-dropping evidence comes from meteorites called chondrites. Some contain tiny, magnetized regions where the field strength was 50 times stronger than the surrounding disk, like finding fossilized tornadoes in a prehistoric wind map. These hotspots likely formed near the young sun's magnetic loops, where plasma jets and flares concentrated the field into intense knots. Over time, these knots could have acted as gravitational seeds, pulling in material to form the first planetary building blocks. So when you hold a meteorite, you're not just holding a piece of space rock, you're cradling a magnetic snapshot of the very forces that built our cosmic neighborhood. Those unassuming fragments tell a story of invisible fields guiding dust into worlds, of chaos tamed into orbits, and of a solar system that could have turned out completely different had magnetism not been there to whisper directions to the raw materials of planets. Billions of light years from Earth, quasars shine as the universe's ultimate lighthouses, blazing cores of galaxies where supermassive black holes devour matter with such ferocity they outshine entire galaxies. Yet hidden within their brilliant light lies a secret code written in the language of magnetic fields. When quasar light passes through clouds of magnetized gas on its epic journey across the cosmos, something remarkable happens. The light becomes polarized, its waves forced to vibrate in a preferred direction like sunlight glinting off the ocean. This subtle fingerprint, invisible to human eyes, has become one of astronomy's most powerful tools, not just for studying quasars themselves, but for mapping the very fabric of the expanding universe. Picture a quasar's light as a chaotic crowd of photons rushing toward Earth. As these particles encounter magnetized regions of intergalactic space, the field lines act like cosmic comb, aligning some photons while letting others pass untouched. The result, light that's slightly polarized, a bias in the orientation of its electromagnetic waves detectable with specialized instruments. By analyzing thousands of quasars, astronomers have discovered these polarization patterns aren't random. They form vast, coherent structures tracing the magnetic skeleton of the cosmic web, revealing where galaxies cluster and where voids stretch empty across billions of light years. Recent surveys like the Sloan Digital Sky Survey's Quasar Catalog have turned this phenomenon into a precision science. Using spectropolarimetry, a technique that splits light into its component wavelengths while measuring polarization, teams have mapped magnetic fields 10 times farther than ever before. One stunning finding: these fields appear to align over distances so vast, they challenge our understanding of how magnetism operates on cosmic scales. Some filaments show coherent polarization across hundreds of millions of light-years, suggesting magnetic forces might have played a role in shaping the universe's large-scale structure from its earliest epochs. But the real magic happens when astronomers combine polarization data with another quasar trait, redshift. As the universe expands, quasar light stretches toward redder wavelengths, with more distant objects showing greater redshift. By comparing polarization patterns across different redshifts, scientists have created a 3D magnetic map of the cosmos, essentially a time-lapse of how magnetic fields have evolved alongside galactic superclusters over billions of years. The resulting animations reveal something unexpected: regions where polarization vectors swirl like cosmic whirlpools, marking spots where galaxies are likely to form in the future. Perhaps most mind-bending is how these measurements refine our grasp of the universe's expansion rate. Polarized light from quasars provides an independent check on dark energy's influence, free from the assumptions baked into other methods. When light passes through magnetized gas, it acquires a tiny delay called Faraday rotation, an effect directly tied to the density of material along its path. By correlating these delays across thousands of quasars, astronomers can essentially weigh the cosmic web, putting new constraints on how fast space itself is stretching apart. What began as a curious property of quasar light has blossomed into an entire field of cosmic cartography. Each polarized photon serves as both messenger and mapmaker, carrying encrypted details about every magnetized cloud it traversed during its billion-year journey. As telescopes grow more sensitive, these subtle magnetic whispers promise to reveal even deeper truths about the birth of galaxies, the nature of dark matter, and perhaps even clues to why our universe's expansion keeps accelerating into the void. Hidden within the cold darkness of interstellar space, molecular clouds teeter on a cosmic tightrope, caught between the crushing force of gravity and an invisible counterbalance that keeps them from collapsing too quickly. These vast stellar nurseries should, by all rights, collapse into stars almost instantly under their own weight. Yet observations reveal a slower, more measured pace of star birth, one that allows massive stars to form without gobbling up all available gas before planets can take shape. The unsung hero behind this delicate equilibrium: magnetic fields weaving through the gas like cosmic rebar, providing just enough resistance to gravity's relentless pull. Walk through the Taurus molecular cloud, one of the closest star-forming regions to Earth, and you'll find a textbook example of magnetic moderation. Here, measurements from radio telescopes reveal field strengths around 50 microgauss, seemingly weak by Earth standards, but over light years of cloud volume, that adds up to an immense stabilizing force. Gravity still wins eventually, but the magnetic fields act like a braking system, ensuring the gas collapses slowly enough to fragment into well-spaced stellar embryos rather than one monstrous star. When astronomers map the cloud's structure, they find elongated filaments precisely aligned with magnetic field lines, nature's way of showing how these invisible forces shape the very architecture of star birth. But not all galaxies play by these rules. Look at starburst galaxies like Messier 82, where stars form at rates 10 times faster than in our Milky Way, and you'll witness what happens when magnetism loses its grip. In these chaotic environments, turbulent gas motions overwhelm the magnetic fields, stripping away their ability to regulate collapse. The result: a frenzied star-making spree where massive stars ignite so densely, their combined radiation blows away remaining gas before smaller stars and potentially their planets get a chance to form. It's the difference between a controlled burn and a wildfire. One leaves behind a diverse planetary system, the other a galactic wasteland littered with short-lived stellar giants. The math behind this balancing act is exquisite. For a molecular cloud to resist rapid collapse, its magnetic energy must roughly equal its gravitational potential energy, a condition astronomers call magnetically subcritical. Taurus hovers near this sweet spot, its fields strong enough to slow contraction but not so rigid that they prevent star formation entirely. Meanwhile, in starburst environments, the ratio tips violently toward gravity, with magnetic pressure accounting for less than 10% of the opposing force. Supercomputer simulations perfectly replicate this dichotomy. When researchers dial up magnetic fields in their models, star formation rates plummet as gas gets stuck in magnetically supported structures. This cosmic tug-of-war has profound implications for life's chances in the universe. Slower star formation allows for a richer mix of stellar masses, including long-lived sun-like stars that give planets billions of years to develop biology. It also prevents gas from being locked up in short-lived massive stars that explode as supernova too quickly. The fact that our solar system emerged from a magnetically moderated cloud like Taurus might be no coincidence. It could be a prerequisite for stable planetary systems capable of nurturing life. As telescopes probe more star-forming regions across the galaxy, a pattern emerges. Where magnetic fields rule, star birth is a symphony. Where they're overpowered, it's a cacophony with no time for planetary crescendos. Some of the most violent explosions in the universe don't come from chemical reactions or nuclear fusion. They erupt when magnetic field lines cross paths in the ultimate cosmic short circuit. Picture two stretched rubber bands pressed together until they suddenly snap. That's magnetic reconnection in action, a fundamental process that unleashes pent-up energy across the cosmos in the blink of an eye. The sun gives us front-row seats to this phenomenon every time a solar flare erupts. Beneath its seemingly calm surface, the sun's plasma stews with tangled magnetic fields. When opposing field lines get pressed together, whether by rising plasma bubbles or collisions between magnetic domains, they don't just peacefully merge. The field lines violently break and reconnect in new configurations, like two zippers forced together and then ripped apart. In that moment, energy equivalent to millions of hydrogen bombs converts from magnetic storage into explosive heat and motion. The flare's sudden brightness comes from plasma heated to tens of millions of degrees, while charged particles get catapulted outward at nearly light speed. Laboratory experiments on Earth reveal just how peculiar this process is. In devices like Princeton's magnetic reconnection experiment, physicists recreate scaled-down versions of cosmic magnetic fields using powerful electromagnets and superheated plasma. High-speed cameras capture the precise moment when field lines rupture, and instability forms where the opposing fields meet, thinning the current sheet until electrons can no longer follow the magnetic contours. Like a dam bursting, the stored energy floods outward in waves, accelerating particles to extreme velocities. What's astonishing is how quickly it happens. Reconnection events in both labs and space often occur thousands of times faster than standard plasma physics predicts, suggesting some hidden mechanism turbocharges the process. Spacecraft like NASA's magnetospheric multiscale mission have flown through natural reconnection sites near Earth, taking measurements every 30 milliseconds. Their findings show these events aren't chaotic but highly organized. Electrons get flung outward in narrow jets while ions form crescent-shaped distributions, telltale signatures of a precise, if violent, energy conversion. The same fundamental process plays out whether in a lab device the size of a room or a solar flare larger than our planet. These explosions don't just make pretty auroras, they shape entire star systems. Around young stars, magnetic reconnection regulates how quickly the protoplanetary disk feeds material to the growing star. In distant galaxies, it may power mysterious fast radio bursts, the most energetic millisecond flashes in the universe. Even Earth's technological infrastructure feels its effects, as reconnection-driven geomagnetic storms occasionally fry satellites and knock out power grids. From the smallest plasma experiments to the grandest astrophysical fireworks, this universal process proves that when magnetic fields tangle, the universe responds with spectacular violence. Deep in the cosmic void where traditional navigation fails, nature offers an extraordinary solution. Celestial lighthouses spinning with such perfect rhythm, their pulses could guide spacecraft across the galaxy. These aren't ordinary stars, they're pulsars, neutron stars beaming radiation from their magnetic poles like interstellar metronomes, some ticking with atomic clock precision over millions of years. Imagine a GPS system where the satellites weigh more than our sun yet spin faster than a kitchen blender, their flashing signals cutting through the noise of deep space with unmistakable clarity. NASA's NICER experiment aboard the International Space Station has already proven the potential. This washing machine-sized instrument locks onto pulsars like cosmic stopwatches, measuring X-ray flashes so predictable they rival Earth's most accurate timekeepers. In 2017, NICER demonstrated something revolutionary. By tracking just 4 pulsars, it could pinpoint the station's position in space within 5 kilometers, all without a single ground-based reference. That's like navigating from New York to Paris using only the steady flicker of distant stellar corpses as your guideposts. But why pulsars? Unlike Earth's GPS satellites, which require constant corrections from ground stations, these natural beacons operate independently. Each pulsar's spin rate is as unique as a fingerprint. Some tick hundreds of times per second, while others lumber along with majestic, seconds-long pauses between pulses. Their signals slice cleanly through the dust and gas that scramble radio waves, making them ideal for regions where conventional navigation fails. Even more astonishing, their lighthouse beams originate from magnetic fields so intense, they twist spacetime itself, creating subtle distortions in pulse arrival times that advanced algorithms can decode to determine a spacecraft's velocity and position in 3 dimensions. The implications for interstellar travel are staggering. Future probes venturing beyond the heliosphere won't have the luxury of calling home for course corrections. Instead, they could carry pulsar maps, precise catalogs of known neutron stars and their pulse signatures. By comparing onboard observations to these maps, a ship light years from Earth could triangulate its position autonomously, like ancient mariners using stars, except these celestial signposts never set or drift. Engineers envision spacecraft with featherweight X-ray telescopes no larger than a dinner plate, their detectors tuned to the harsh but reliable glow of pulsar beams. Yet challenges remain. While millisecond pulsars are phenomenally stable, they're not perfectly so. Glitches, sudden speed-ups in spin, can occur when a pulsar's crust cracks under magnetic stress. Teams at NASA and ESA are developing machine learning systems to filter out these anomalies, distinguishing true navigation signals from cosmic noise. There's also the issue of signal strength. Pulsar X-rays are faint by the time they reach us, requiring sensitive detectors. But progress is rapid. Recent tests with modulated X-ray lasers show how artificial pulsar-like signals could one day guide rovers on the far side of the Moon or Mars, where Earth's GPS signals can't reach. What began as a curious astronomical phenomenon has blossomed into humanity's potential ticket to the stars. These spinning relics of dead stars, once seen as mere astrophysical oddities, may light the way for future generations sailing the interstellar ocean. In their relentless ticking, we find not just the heartbeat of collapsed stars, but perhaps the rhythm by which our descendants will chart their course to the cosmos. When galaxy clusters collide, they don't just pass through each other like ghosts, they tear the fabric of space apart in slow motion, creating shockwaves of such violence that they turn the entire region into a particle accelerator the size of millions of light years. The Bullet Cluster, arguably the most famous cosmic collision ever captured by telescopes, shows this process in spectacular detail. X-ray images reveal a bullet-shaped cloud of 100 million degree gas, the aftermath of two clusters plowing through each other at speeds approaching 2,500 kilometers per second. But it's the radio observations that unveil the hidden drama. Vast filamentary structures glowing with synchrotron radiation, tracing where shockwaves have amplified magnetic fields to strength rivaling those around neutron stars. These collisions create conditions impossible to replicate anywhere else in the universe. As the clusters merge, their diffuse plasma gets squeezed between the clashing galaxies like water between colliding ships, compressing and twisting the embedded magnetic fields into ropes of energy. Computer simulations show these fields don't just get stronger, they reorganize entirely, forming intricate webs where field lines are stretched, folded, and snapped like cosmic rubber bands. The most intense activity happens where the cluster's dark matter components detected through gravitational lensing have already sailed ahead of the gas, leaving behind a battlefield of turbulent plasma. Here, magnetic fields act like cosmic dynamos, converting the kinetic energy of the collision into electromagnetic fury. What makes the Bullet Cluster so special is the smoking gun evidence it provides. Radio telescopes detected something extraordinary, an edge, where the magnetic field strength jumps by a factor of 10 across the shock front. It's as if someone drew a line in space separating normal conditions from a zone where magnetism dominates. This transition happens over just 200,000 light-years, a blink in cosmic terms, with electrons accelerated to nearly light speed along the shock boundary. The resulting radio emission forms a perfect arc, like a celestial bow wave frozen in time, but the real surprise came when astronomers compared different wavelengths. X-rays show where ordinary matter heats to extreme temperatures, while radio waves map the magnetic chaos. In most of the cluster, these overlap, but in the wake of the collision, they separate dramatically, revealing how magnetic fields can decouple from gas and persist long after the visible fireworks fade. This proves magnetic fields aren't just passive passengers in galaxy clusters, they're resilient structures that can outlast even the most violent encounters, potentially seeding future cosmic evolution. These amplified fields don't just make for pretty pictures, they fundamentally alter how galaxies interact. The enhanced magnetism acts like a cosmic glue, preventing stripped gas from drifting away entirely and providing scaffolding for new star formation. Some theorists speculate that without these post-collision magnetic structures, the universe's largest clusters would be far more disordered, their member galaxies scattered like leaves in the wind. Instead, they find their way back to equilibrium, guided by invisible magnetic hands stretching across the void. The Bullet Cluster offers more than just a snapshot of destruction. It's a living laboratory showing how the universe rebuilds after catastrophe. Those luminous radio arcs are nature's way of proving that even in chaos, magnetism provides the architecture for cosmic rebirth, turning violent collisions into cradles for new magnetic megastructures that may shape galaxies for billions of years to come. Even in the emptiest reaches of space, dust doesn't drift aimlessly. It lines up like disciplined soldiers, silently shaping the light that passes through it. These microscopic grains, no larger than a wavelength of light, become nature's own compass needles, spinning until they lock into alignment with the Milky Way's magnetic field. The result, a phenomenon called starlight polarization, where the light we see from distant stars carries hidden fingerprints of every magnetic field it traversed. Think of it like sunlight glinting off the surface of a pond, except instead of water molecules reflecting light, it's interstellar dust subtly twisting the light's orientation across light-years of space. The Planck Space Telescope transformed this curiosity into a cosmic cartography tool. By meticulously measuring the polarization of starlight across the entire sky, it revealed something astonishing. The Milky Way isn't just sprinkled with random dust clouds. It's threaded with a vast, organized magnetic skeleton, its field lines tracing the spiral arms like ink on a cosmic blueprint. Some regions show fields stretched taut along filaments of gas, while others twist into elegant loops near stellar nurseries, proof that magnetism isn't just present in our galaxy, it's architecting its very structure. Here's how the magic works. Each interstellar dust grain contains a tiny bit of iron or other magnetic minerals. When a passing star's radiation sets them spinning, the galaxy's magnetic field acts like a cosmic brake, slowing their rotation until they settle with their long axis perpendicular to the field lines. Like countless tiny antennas, these aligned grains then preferentially absorb starlight, vibrating in one direction while letting perpendicular light pass, polarizing it by just a few percent, but enough for sensitive instruments to detect. The real breakthrough came when Planck combined polarization data with other wavelengths. In the constellation Orion, for example, polarization vectors curve gracefully around the edges of giant molecular clouds, mapping where magnetic pressure contains star-forming gas like an invisible cage. Near the galactic center, the pattern shifts dramatically. Field lines bunch up like spaghetti squeezed through a fist, revealing the violent tug of war between gravity and magnetism at our galaxy's heart. These maps aren't static, they capture a dynamic system where magnetic fields channel star formation, then get reshaped by the very stars they helped create. What makes this discovery revolutionary is its scale. Planck's all-sky survey shows magnetic coherence over thousands of light years, proving these fields aren't local quirks but galactic-scale forces. Some filaments maintain alignment across distances so vast, they must be shaped by processes we're only beginning to understand, perhaps relics from the Milky Way's violent birth, or remnants of primordial magnetism woven into the universe's fabric since the Big Bang. For astronomers, this polarized dust does more than reveal magnetic fields. It helps peel back layers of cosmic deception. When studying the cosmic microwave background, the afterglow of the Big Bang, polarized galactic dust once posed an annoying contaminant. Now, thanks to Planck's meticulous mapping, scientists can subtract this foreground like wiping fog from a window, bringing the universe's earliest light into sharper focus than ever before. So the next time you gaze at the Milky Way's hazy band across the night sky, remember, its faint glow isn't just unfiltered starlight. It's light that's been gently molded by trillions of dust grains, all pointing the way to the invisible magnetic forces weaving our galaxy together, one aligned particle at a time. At the universe's birth, mere fractions of a second after the Big Bang, space itself may have writhed with magnetic fields stronger than anything in existence today, fields so powerful they could have stretched across the entire cosmos in an instant during inflation. While these primordial fields likely faded as the universe expanded, they might have left faint scars in the oldest light we can observe, the cosmic microwave background. This afterglow, released when the universe was just 380,000 years old, carries subtle patterns that could be magnetic fingerprints from the dawn of time. Telescopes like the upcoming Simons Observatory in Chile's Atacama Desert are now hunting for these elusive signatures with unprecedented sensitivity. Unlike traditional CMB studies that focus on temperature fluctuations, these next-generation instruments analyze the light's polarization, its preferred vibration direction, with nanometer precision. The telltale sign would be a specific swirl pattern called B-mode polarization, a twisting in the light that ordinary density variations couldn't produce. If detected, these swirls would be the smoking gun for primordial magnetism, etched into the fabric of space before the first stars flickered to life. The challenge lies in separating this signal from later interference. Galactic dust and gravitational lensing also polarize the CMB, creating false swirls that mimic primordial imprints. That's where the Simons Observatory's multi-frequency approach becomes crucial. Its array of 50,000 detectors will map the sky at multiple wavelengths, letting scientists subtract the dust's contaminating glow like peeling layers off an onion. Any remaining B modes at the largest angular scales patterns spanning degrees on the sky could point directly to inflation's magnetic handiwork. Theorists have calculated what these fields might look like if they survived. Unlike today's tangled galactic fields, primordial magnetism would be eerily uniform, woven into the universe's structure like threads in a tapestry. Their strength would be unimaginably weak by current standards, 1 billion times fainter than Earth's magnetic field, but their scale would be cosmic, potentially spanning the entire observable universe in a coherent web. Some models even suggest these fields could have acted as seeds for the larger structures we see today, guiding where galaxies eventually formed through subtle gravitational nudges millions of years later. Detecting these imprints wouldn't just rewrite cosmology textbooks, it would unveil entirely new physics. Standard models of inflation don't predict strong primordial fields, so their discovery might hint at exotic processes like phase transitions in the early universe or even relics from higher dimensional theories. The Simons Observatory, set to begin full operations in 2025, could soon turn this speculation into solid data. Every subtle twist in the ancient light it captures might carry echoes of magnetism's first moments, written across the sky in the universe's oldest handwriting, waiting to be decoded. When a star like our Sun nears the end of its life, it doesn't just fade quietly, it throws off its outer layers in a final, dramatic exhale. But instead of expanding evenly like a balloon, these stellar winds twist into breathtakingly intricate shapes, glowing hourglasses, spirals, even delicate cosmic butterflies. The secret behind this artistic display, magnetic fields acting like celestial sculptors, channeling the dying star's outburst into patterns more elaborate than anything gravity alone could create. Take the Cat's Eye Nebula, one of the most complex planetary nebulae ever observed. At its heart lies a hot, exposed stellar core blasting winds at over 4 million miles per hour. Left to gravity alone, this material should flow outward in a simple sphere, but Hubble's razor-sharp images reveal something far more structured: concentric rings, jet-like streamers, and a central double-lobed shape resembling an hourglass. The only force capable of imposing such geometry on this chaos is magnetism. Observations show the central star's field is 1,000 times stronger than our Sun's, funneling the escaping gas along its lines like iron filings aligning around a bar magnet. The difference between magnetic and non-magnetic stellar deaths becomes obvious when comparing nebulae. NGC 4380, for example, shows a nearly perfect spherical shell, the hallmark of a star whose winds expanded freely without magnetic guidance. Contrast this with the Southern Crab Nebula, where tightly collimated jets punch through glowing gas lobes, forming an unmistakable hourglass. The key distinction lies in the central star's rotation. Slow rotators die with symmetrical, spherical ejections, while stars that spun faster during their lives amplify their magnetic fields through dynamo effects, turning their deaths into spectacles of cosmic origami. Here's where it gets even wilder. Some stars don't just have orderly magnetic fields, they fling spirals of gas into space like cosmic sprinklers. The star our Sculptoris does this with eerie precision, its magnetic field locking step with its 12-year pulsation cycle to eject material in a perfect three-dimensional spiral. ALMA radio telescopes captured this structure in stunning detail, showing how magnetism can impose rhythm on even the most violent stellar processes. These spirals aren't just beautiful, they're time capsules, with each loop representing another pulse in the star's final millennia. But perhaps the most dramatic magnetic sculpting occurs in binary systems, where two stars dance close enough to intertwine their winds. The Red Rectangle Nebula showcases this beautifully. Its namesake shape comes from one star's magnetically channeled winds colliding with its companion's outflow, creating geometric shock patterns that glow like neon signage in space. Without magnetic fields, this interaction would resemble a chaotic splash rather than a precise crystalline structure. These celestial artworks do more than dazzle astronomers. They're reshaping our understanding of stellar life cycles. By studying the magnetic fingerprints in these nebulae, scientists can reconstruct a star's final chapters, its rotation rate, the strength of its hidden dynamo, even whether it hosted unseen planets whose gravity may have influenced the outflow. Every swirling pattern is a cosmic autopsy report written in the language of magnetic fields and stellar winds. Dark matter has always played by its own rules, invisible, mysterious, and seemingly indifferent to the magnetic forces that shape ordinary matter. But what if we've been wrong all along? Some physicists are now daring to suggest the unthinkable, that dark matter might actually feel magnetism after all. Not the magnetism we know, but a shadow version of it operating under rules we've yet to fully comprehend. This radical idea could solve one of cosmology's most stubborn puzzles: why certain small galaxies behave as if their dark matter is clumping together in ways our standard models can't explain. Take the dwarf galaxies orbiting our Milky Way. These cosmic runts should be evenly filled with dark matter, their invisible halos smoothly distributed according to simulations. Yet observations tell a different story. In galaxies like Triangulum II and Draco, the dark matter appears densely packed at their cores, almost as if some unseen force is corralling it there. Traditional gravity alone can't explain this anomaly, but introduce a hypothetical dark magnetic force, and suddenly the pieces start fitting together. Picture dark matter particles as cosmic cattle, herded into tight clusters by invisible magnetic fences woven from a dark sector of physics we've barely begun to explore. The math behind this gets wild. If dark matter possesses even a faint electromagnetic-like interaction, what theorists call dark photons, these particles could effectively create their own version of magnetic fields. Unlike the familiar fields generated by moving electrons, dark magnetism would arise from the dance of hidden particles we've never directly detected. Their influence would be subtle but profound, gently nudging dark matter into denser configurations over billions of years, while remaining completely transparent to ordinary matter. It's like two parallel universes of magnetism coexisting in the same space, one we can see and measure and another operating in the shadows. Critics argue this is speculative at best, a band-aid for gaps in our understanding. Yet intriguing clues keep surfacing. When astronomers mapped the motions of stars in the oddball galaxy NGC 1052 DF2, they found barely any dark matter at all, as if something had swept it clean. A competing team later claimed the opposite, highlighting how messy the evidence remains. But if dark magnetism exists, it might explain both extremes, sometimes clumping dark matter tightly, other times scattering it like iron filings near a powerful magnet. Experiments are already hunting for proof. CERN SPS Accelerator has begun shooting protons into targets, searching for signs of dark photons that could mediate this shadow magnetism. Meanwhile, ultrasensitive lab experiments like ADMX listen for actions hypothetical dark matter particles that might interact weakly with magnetic fields. The stakes couldn't be higher. If confirmed, dark magnetism would force us to rewrite cosmology's rulebook, revealing an entire hidden dimension of forces shaping galaxies right under our noses. Until then, these ideas remain at the frontier, equal parts thrilling and contentious. They remind us that for all our cosmic maps and theories, the universe still holds cards it hasn't shown. Whether dark matter dances to a magnetic tune or not, one thing is certain: the galaxies whispering these secrets aren't done surprising us yet. Jupiter's icy moon Europa shouldn't stand a chance at hosting life. It's bombarded by radiation, frozen solid on the surface and far from the sun's warmth. Yet beneath its cracked icy shell lies one of the most promising places to search for alien life in our solar system. How does this cosmic contradiction work? Europa owes its potential entirely to Jupiter's monstrous magnetic field, a planetary force field stretching millions of miles into space, diverting the worst of the solar wind's deadly particles. Without this protection, Europa's subsurface ocean would be sterilized by radiation, its chemistry scrambled beyond recognition. This cosmic shelter system isn't unique to Europa. Across the galaxy, exomoons orbiting gas giants could enjoy similar protection if their host planets sport strong enough magnetic fields. The TRAPPIST-1 system, with its 7 Earth-sized worlds crammed closer than Mercury orbits our Sun, poses a fascinating case study. 3 of these planets sit in the habitable zone where liquid water could exist, but their tight orbits around a tiny red dwarf star leave them vulnerable to brutal stellar flares hundreds of times stronger than anything our Sun produces. Here's the twist: if any of these worlds host moons, and current models suggest they likely do, those exomoons might actually be safer than the planets they orbit, provided their gas giant hosts generate robust magnetic bubbles. Red dwarfs like TRAPPIST-1 are notorious for their violent youth, bombarding nearby planets with radiation for billions of years. But a gas giant's magnetic field could create a safe harbor, deflecting charged particles like an umbrella in a hailstorm. Computer simulations show that under the right conditions, an exomoon's shielded side could maintain habitable conditions even as its host planet gets scorched. The key variable, the gas giant's rotation speed. Faster spin means stronger dynamo action in the planet's core, amplifying its magnetic shield exactly as Jupiter's 10-hour rotation does for Europa. There's tantalizing indirect evidence this might already be happening. When the Hubble Space Telescope observed TRAPPIST-1 planets passing in front of their star, it detected odd variations in light that some astronomers interpret as possible magnetic interactions, signatures of unseen giant planets with protective magnetospheres large enough to distort starlight. If confirmed, any moons orbiting these worlds would sit in radiation shadows, their surfaces potentially bathed in the gentle glow of auroras created by particles spiraling along magnetic field lines rather than the full brunt of stellar flares. The implications rewrite the rules for habitable worlds. We've long assumed Earth-like planets were the best candidates for life, but magnetic shielding suggests life might have better odds on exomoons, especially around temperamental red dwarfs. Europa shows us that even in hostile environments, a gas giant's magnetic umbrella can maintain stable conditions for billions of years, allowing chemistry to progress toward biology in protected subsurface oceans. As next-generation telescopes like the Extremely Large Telescope come online, they'll scrutinize TRAPPIST-1 not just for planetary atmospheres, but for the telltale radio emissions that betray the presence of magnetic giants and possibly their sheltered, life-friendly moons. When a dying star commits the ultimate cosmic suicide, collapsing into a black hole or neutron star, its final scream isn't a whimper, but a blast of gamma rays so powerful it briefly outshines entire galaxies. Yet these gamma-ray bursts, the universe's most violent explosions, don't radiate evenly in all directions. Instead, they fire focused beams tighter than a laser pointer, visible billions of light-years away. The secret behind this precision targeting, magnetic fields acting as cosmic gun barrels, channeling chaos into disciplined streams of annihilation. Picture the final moments of a massive star's core collapse. As matter rushes inward at nearly light speed, it doesn't just pile up quietly, it twists into a hyper-fast rotating disk, winding magnetic field lines into a helical coil around the newborn black hole like a cosmic spring. These fields don't just passively observe the destruction, they become particle accelerators of unimaginable scale. Charged material gets whipped along the magnetic spirals, while the field's own tension squeezes the outflow into twin jets thinner than a straw held at arm's length but stretching millions of miles. The result is a death beam concentrated into less than 5 degrees of sky so narrow that for every burst we see, there are hundreds pointed elsewhere in the cosmos, invisible to our telescopes. This extreme collimation explains one of gamma-ray bursts' greatest mysteries, how they're detectable across such vast distances. The burst GRB 2200-109A, spotted in 2022, originated from a galaxy over 2 billion light-years away, yet for a few seconds, it flooded Earth's detectors with more energy than our Sun will emit in its entire 10-billion-year lifetime. If that energy had sprayed uniformly in all directions, the intensity would have dropped off too quickly with distance. But focused into a razor-thin beam, the radiation remains lethal across cosmic scales, like a lighthouse visible from another continent because its light doesn't disperse. Astrophysicists confirmed this mechanism using polarization measurements. When light from a gamma-ray burst passes through interstellar magnetic fields, its waves align in specific orientations. A fingerprint only possible if the emission originated from highly organized magnetic structures near the burst. Observations of GRB 021206 revealed polarization levels exceeding 60%, proving the beams weren't just narrow but magnetically disciplined, like bullets rifled by a cosmic barrel. But here's where it gets even stranger. These magnetic nozzles might also explain why some bursts last milliseconds while others glow for minutes. Short gamma-ray bursts believed to come from colliding neutron stars likely have simpler magnetic geometries, quick snapshots of fields torn apart in the merger's violence. Long bursts born from collapsing stars sustain their beams by continuously drawing energy from the black hole's accretion disk, like a fire hose fed by an endless reservoir. Some theorists argue the magnetic fields even self-repair during these events, with turbulence in the jet generating new field structures that prevent the beam from dispersing too quickly. The implications stretch far beyond astrophysics. If intelligent life exists elsewhere in the universe, gamma-ray bursts pose an existential threat. A rogue beam could sterilize a planet thousands of light-years away. Thankfully, Earth's magnetic field and atmosphere offer some protection, but civilizations in galaxies experiencing frequent bursts might face evolutionary hurdles we've never contemplated. These magnetic death beams don't just light up the cosmos, they may silently dictate where life gets a chance to thrive at all. Some of the most bizarre and powerful objects in the universe might be hiding in plain sight, not as stars or black holes, but as cosmic scars left over from the Big Bang itself. Imagine space-time not as a smooth fabric, but as a tangled web of one-dimensional defects called cosmic strings, infinitely thin threads of pure energy stretching across the universe, thinner than a proton but with the mass of Mount Everest crammed into every inch. If they exist, these relics from the universe's first moments would warp space around them with unimaginable gravitational forces, and according to cutting-edge theories, they might also be wrapped in coils of ultra-strong magnetic fields, turning them into invisible cosmic lightning rods humming with power. String theory paints a vivid picture of how this could work. In the early universe, when fundamental forces were merging and splitting in rapid succession, tiny loops of energy might have gotten frozen into the fabric of reality as phase transitions rippled through space. These defects wouldn't behave like ordinary matter, they'd be pure topological knots in space-time itself. But here's the twist: as they vibrate, snap, and reconnect across billions of years, they could generate magnetic fields strong enough to tear atoms apart. Picture a guitar string vibrating underwater. Except this string is a billion light-years long, and its music is a symphony of particle acceleration and gamma-ray bursts. The smoking gun for these magnetic monsters might already be hiding in our telescopes. Some astronomers argue that fast radio bursts, those mysterious millisecond flashes from distant galaxies, could be cosmic strings snapping like overstretched rubber bands. When two segments of a string cross and annihilate, the energy release would channel along the string's length, launching ultra-relativistic jets packed with charged particles. The resulting shockwaves would amplify any ambient magnetic fields to strengths dwarfing neutron stars, creating the perfect conditions to generate the bizarre polarization signatures we've detected in some bursts. Even more tantalizing are the gravitational lensing anomalies that keep popping up in deep field surveys. Certain distorted galaxies appear stretched in ways that don't match conventional dark matter distributions, almost as if an invisible, razor-thin filament were warping space between them. If these turn out to be cosmic strings, their predicted magnetic halos could explain another puzzle: the inexplicably uniform magnetic fields we've detected spanning entire galaxy clusters. Strings threading through these regions would act like cosmic sewing needles, stitching coherent field lines across millions of light-years while remaining nearly undetectable themselves. The hunt is now on for more direct evidence. Next-generation gravitational wave detectors like LISA could spot the distinctive chirp of a string loop collapsing, a signal that would ripple space-time differently than black hole mergers. Meanwhile, radio astronomers are scanning the cosmic microwave background for telltale discontinuities, sharp edges in the primordial light's polarization that might trace back to strings slicing through the early universe. Every unexplained magnetic anomaly in deep space brings us closer to answering one of cosmology's wildest what-ifs: that the universe isn't just held together by gravity and dark matter, but by invisible, magnetized scars from its violent birth, threads woven through reality itself. At the heart of our Milky Way, where stars crowd so thickly they blend into a golden haze, something even stranger hides in plain sight: an eerie network of magnetized filaments stretching like cosmic spiderwebs around our galaxy's supermassive black hole. The Magnetism radio telescope in South Africa peeled back the veil on these structures, revealing hundreds of them, each one a slender thread of energized particles, some stretching 150 light-years end to end, yet no wider than a starship's length. They hover almost motionless near Sagittarius A, the 4 million solar mass black hole anchoring our galaxy, their perfect alignment defying every expectation of cosmic chaos. What makes these filaments so baffling isn't just their existence, it's how they're arranged. Unlike the tangled mess near most black holes, these filaments run almost parallel, like strings on a harp, spaced with unnatural regularity. Some resemble cometary tails, pointing directly away from the galactic center as if blown by a relentless wind. Others curve gently, tracing arcs that suggest an invisible force field shaping their path. The most striking feature, their polarization. Mercator's observations show their radio waves are highly polarized, a dead giveaway that electrons are spiraling along tightly wound magnetic field lines at nearly light speed, turning each filament into a natural particle accelerator. Now here's the million-dollar question: are these filaments the black hole's doing, or something even weirder? One leading theory paints Sagittarius as a cosmic puppeteer. Every few centuries, our black hole likely swallows a star or gas cloud in a violent feeding frenzy. These meals could trigger explosive outbursts, sending shockwaves racing through surrounding magnetic fields. The filaments might be scars from these eruptions, magnetic tubes where particles got trapped and accelerated, glowing long after the initial explosion faded. Supporting this, astronomers have spotted similar, shorter filaments near other active black holes, like a scaled-down version in galaxy M87. But there's a competing idea that's even more radical. What if these filaments aren't products of the black hole at all, but relics of a far older process? Their sheer length and uniformity suggest they could be fossil structures, leftovers from a time when magnetic fields from the Milky Way's formation got stretched and amplified by the black hole's gravity over billions of years. Imagine the galaxy's earliest magnetic field lines frozen into place, like wrinkles in a carpet, smoothed but never erased. This would make them cosmic archaeologists' gold, preserving a record of magnetic conditions when our galaxy was young. The truth might lie in their energy signature. Some filaments blaze with synchrotron radiation, their electrons clearly accelerated by recent events. Others appear dark and quiet, their particles having gradually leaked away over millennia. This mix of young and old hints at an ongoing process, perhaps the black hole periodically re-energizing ancient magnetic skeletons with fresh bursts of activity. Recent observations even caught one filament flickering over months, as if current were suddenly surging through it like a live wire. Whatever their origin, these filaments are rewriting how we see black hole environments. They prove that even in the most extreme gravitational arenas, magnetism can impose order, creating structures durable enough to outlast stars and subtle enough to trace forces we've barely begun to understand. Far from being destructive monsters, black holes might also be cosmic weavers, spinning magnetic threads that stretch across the galactic loom, silent witnesses to the invisible forces shaping our corner of the universe. Some stars don't just flicker, they rewrite their own cosmic rulebooks in real time, flipping their magnetic poles with all the predictability of a tossed coin. Take Tau Boötis, a star just 51 light-years away that casually swapped its north and south magnetic poles while astronomers watched in disbelief. Unlike our Sun's orderly 11-year polarity reversal, this stellar oddball performed its magnetic backflip in less than a year, a blink in cosmic terms before settling back only to flip again unexpectedly. It's as if someone keeps hitting the reset button on a celestial compass, turning what should be a stable stellar feature into a cosmic slot machine. Earth plays this game too, but on geological timescales. Our planet's last full magnetic reversal happened 780,000 years ago, when compass needles would have pointed south instead of north for a few thousand chaotic years. Sediment records show these flips aren't clean switches. The field weakens, develops multiple poles like a poorly magnetized bar, then finally settles into its new orientation. Scientists drilling into ancient lava flows have mapped these transitions in stunning detail, with magnetic minerals freezing the field's turbulent state at the moment the rock solidified. Some reversals take as little as a century, while others drag on for millennia, a reminder that even Earth's mighty dynamo occasionally stumbles. The stark difference between stellar and planetary reversals reveals fundamental truths about cosmic magnetism. Stars like Tau Boötis flip rapidly because their entire convective zones, the churning outer layers generating magnetic fields, can reorganize at once. Our Sun's more gradual process stems from differential rotation, where equatorial regions spin faster than polar ones, carefully winding up field lines before they snap into reversal. Earth's slower pace comes from the viscous nature of our liquid iron core. It takes time to redirect those slow-moving metallic currents powering our magnetic dynamo. But the real cosmic rebels are magnetic variables like HD 77326, where patches of opposite polarity erupt across the surface like warring factions. Spectropolarimetric images reveal stunning magnetic mosaics, regions with field strengths varying from 0 to 4,000 Gauss compared to Earth's modest half-Gauss field, all on the same star. These chaotic configurations arise when different layers of the star rotate at wildly different speeds, tangling magnetic fields like spaghetti in a blender. The resulting instability can trigger flares 1,000 times more powerful than our Sun's, proving that when magnetism goes rogue, the fireworks follow. What makes these cosmic reversals so fascinating isn't just their unpredictability, it's what they teach us about magnetic sustainability. Earth's occasional stumbles may explain why Mars lost its protective shield when its smaller core solidified. Stars that reverse too violently often strip atmospheres from orbiting planets, while those with steadier fields foster stable systems. As astronomers discover more exoplanets, they're realizing that a star's magnetic personality may be just as important as its size or temperature in determining a world's habitability. Those flickering fields don't just make for interesting observations, they might silently dictate where life gets a foothold in the universe. High above Jupiter's swirling storms, where the solar wind meets the planet's monstrous magnetic field, something extraordinary unfolds. A celestial ballet of plasma, sculpted into rippling waves that stretch wider than Earth itself. These aren't just random swirls, they're Kelvin-Helmholtz instabilities, nature's way of turning chaos into breathtaking order. The Juno spacecraft's close-up images reveal these structures in shocking detail. Vast, curling tendrils of ionized gas cascading along the boundaries of Jupiter's magnetosphere like ocean waves frozen mid-crash. Each undulation tells a story of invisible forces at work, magnetic fields, wrestling with the supersonic stream of charged particles screaming outward from the sun. What makes these plasma waves so mesmerizing is how they mirror phenomena we see on Earth, just scaled up to cosmic proportions. Picture wind whipping across water, creating those familiar rolling ridges on a lake's surface. Now replace the water with superheated plasma and the wind with a solar gale moving at 1,000,000 miles per hour, and you've got the recipe for Jupiter's otherworldly waves. But here's the twist: without magnetic fields, this interaction would be a shapeless mess. It's the planet's immense magnetic grip that organizes the chaos, shepherding the plasma into those eerie, regimented patterns. Juno's ultraviolet spectrograph caught this process in action, showing how charged particles get funneled along magnetic field lines, creating luminous curtains that pulse and ripple with mathematical precision. The scale of these structures defies imagination. Some observed near Jupiter's poles stretch over 6,000 miles from crest to crest, large enough to swallow our planet whole. Their formation relies on a delicate balance between two titanic forces: the magnetosphere's rotation, which flings plasma outward at nearly 200 miles per second, and the solar wind's opposing pressure. When these forces reach a critical threshold, the boundary layer between them goes unstable, buckling into those iconic wave shapes. Computer simulations at NASA, a Goddard Space Flight Center, show the exact moment this happens. Magnetic tension acts like cosmic guitar strings, vibrating at specific frequencies that dictate the wave's spacing and height. But Jupiter isn't alone in this phenomenon. Saturn's magnetosphere hosts similar waves, though smoother and more subdued, a reflection of its less turbulent solar wind environment. Even Earth experiences miniature versions during intense geomagnetic storms, when our magnetosphere gets battered by solar eruptions. The difference lies in the details. Jupiter's waves glow fiercely in X-rays due to highly energetic oxygen and sulfur ions, while Earth's are dominated by hydrogen and helium. These variations serve as cosmic diagnostics, allowing scientists to deduce the composition and dynamics of distant magnetospheres just by studying their instability patterns. The real magic happens when these waves break, not like ocean waves crashing ashore, but through a process called magnetic reconnection. As the Kelvin-Helmholtz curls grow steeper, opposing magnetic field lines get pressed together until they snap like overstretched rubber bands. This unleashes pent-up energy, accelerating particles to near-light speeds and triggering dazzling auroras far below. Juno's team traced one such event directly to a colossal wave breaking near Jupiter's dusk flank, proving these instabilities aren't just pretty to look at, they're fundamental to how planets exchange energy with the space around them. What began as an oddity spotted in early magnetosphere models has blossomed into a universal principle. From the scorching plasma loops on our Sun to the magnetized winds of distant pulsars, Kelvin-Helmholtz waves keep appearing wherever magnetic fields grapple with flowing matter. They're nature's way of finding balance between order and chaos, a reminder that even in the most violent corners of the cosmos, there's an underlying geometry waiting to be revealed. And thanks to spacecraft like Juno, we're finally deciphering its magnetic code. To understand the universe's first magnetic fields, we must rewind to a time before stars, before galaxies, even before atoms existed. Picture the cosmos in its infancy, a seething plasma of particles and energy so dense that light couldn't travel more than a fraction of an inch before scattering. In this primordial soup, the seeds of magnetism were sown through processes so extreme, they defy earthly intuition. One leading theory suggests these fields emerged from quantum fluctuations, tiny, random variations in energy that rippled through the fabric of space-time during the universe's first trillionth of a second. Like invisible ink appearing under heat, these fluctuations could have imprinted magnetic patterns onto the expanding universe during inflation, stretching microscopic whirlpools of charged particles into cosmic-scale fields in the blink of an eye. But there's another, even more dramatic possibility: phase transitions in the early universe. Imagine boiling water suddenly turning to ice, except instead of water, it's the fundamental forces themselves undergoing a metamorphosis. As the universe cooled from trillions of degrees, the electromagnetic force may have separated from the weak nuclear force in a violent shift, a cosmic snap that sent shockwaves through the plasma. These ripples could have twisted free electrons into swirling currents, jump-starting magnetic fields with strengths billions of times greater than anything in today's universe. Supercomputer simulations of this epoch show something astonishing. These newborn fields wouldn't have been random. They'd form vast, organized structures, sheets and filaments of magnetic energy woven through the infant cosmos like threads in a tapestry. The echoes of these primordial fields might still linger. Some cosmologists argue that the faint magnetic fields permeating galaxy clusters, detected through their polarizing effect on ancient light, are too widespread and coherent to have formed locally. Instead, they could be fossils from the universe's first moments, diluted but never erased by 14 billion years of expansion. The Planck spacecraft's observations of the cosmic microwave background add fuel to this idea. Its maps revealed subtle patterns in the light's polarization that some researchers interpret as scars from primordial magnetic turbulence, frozen into place when the universe was just 380,000 years old. The wildest twist, these ancient fields might hold clues to physics beyond our current understanding. Certain grand unified theories predict that exotic particles like magnetic monopoles, hypothetical, isolated north or south poles, could have formed during those early phase transitions. If remnants of these particles persist, they'd leave distinctive signatures in the primordial magnetic field structure. Experiments like the upcoming CMB S4 telescope aim to hunt for these fingerprints with unprecedented precision, potentially uncovering new chapters in the story of cosmic magnetism. What's certain is that magnetism didn't passively emerge with the universe, it helped shape it from the beginning. Those first fields, whether born from quantum chaos or the splitting of fundamental forces, likely guided the flow of matter into the filaments and voids we see today. They might even have nudged the first stars to form, jump-starting the chain of events that led to galaxies, planets, and ultimately us. So when you hold a compass and watch its needle point north, remember, you're not just sensing Earth's magnetic field. You're touching a force that's been weaving through the cosmos since time itself began. Every autumn, the Arctic tern embarks on an impossible journey, flying from pole to pole across 25,000 miles of ocean with nothing but innate instinct to guide it. What's even more astonishing, these featherweight travelers can recalibrate their course mid-flight if scientists artificially shift Earth's magnetic field around them, proving they don't just follow stars or landmarks, they navigate by sensing the planet's invisible magnetic contours. This biological superpower, called magnetoception, turns out to be shockingly common in nature. Sea turtles imprint on the magnetic signature of their birth beach as hatchlings, returning decades later with pinpoint accuracy. Even bacteria align like living compass needles, their internal chains of magnetic minerals pointing them toward oxygen-poor sediments. But here's the cosmic twist. If life evolved this sensitivity under Earth's gentle magnetic embrace, could it exist in places where magnetic forces are 1,000 times stronger, or barely present at all? The mechanics behind magnetoception read like science fiction. Migratory birds appear to harness quantum physics in their eyes. A protein called cryptochrome forms radical pairs when struck by light, and Earth's magnetic field subtly alters how these paired electrons spin. It's as if their retinas contain microscopic compasses that paint the world in magnetic hues we can't perceive. Loggerhead turtles take a different approach. Magnetite crystals in their skulls act like biological bar magnets, physically tugging on specialized cells when aligned with planetary field lines. But neither system evolved for environments like Jupiter's moon Europa, where magnetic fields twist unpredictably under tidal stresses, or exoplanets orbiting red dwarfs blasted by ever-shifting stellar magnetism. Consider the implications for extremophiles in cosmic magnetic maelstroms. Near a magnetar, a neutron star with a magnetic field a quadrillion times Earth's, any life form would need shielding just to prevent its biomolecules from tearing apart. Yet bacteria on Earth thrive in the crushing magnetic fields of MRI machines, suggesting cellular structures might adapt to far stronger forces than we've assumed. The opposite challenge exists on Mars, where the weak, patchy magnetic fields offer little navigational consistency. If Martian microbes exist, they'd need sensors exponentially more sensitive than a turtle's just to orient in their fractured magnetic landscape. Astrobiologists are now testing these limits in labs. By exposing magnetotactic bacteria to simulated exoplanetary conditions, they've found some strains can reorganize their internal compass chains within generations when field strengths change. Even more startling, fruit flies bred for 25 generations in near-zero magnetism develop enhanced sensitivity to extraordinarily weak fields, proof that magnetoception isn't fixed but an evolving trait. This plasticity hints that life might engineer novel magnetic sensors tailored to alien environments, perhaps using superconducting proteins or magnetosensitive ion channels unlike anything on Earth. The deepest mystery isn't whether life can sense magnetism elsewhere, it's what information magnetic fields might carry in different cosmic contexts. On Earth, field lines map predictable geographic features, but near a black hole's accretion disk, they'd writhe like living things, encoding data about plasma densities and gravitational tides. For organisms in such realms, reading magnetic fields could be less about navigation and more like interpreting a dynamic energy landscape, a sixth sense fundamentally alien to our experience. As we search the cosmos for life, magnetoception reminds us that evolution works with the tools at hand, and in a universe threaded with magnetic forces, those tools might paint reality in ways we're only beginning to imagine. When a star like our Sun dies, you'd expect its fading embers to cool quietly into darkness. But some white dwarfs, the dense cores left behind, defy this peaceful retirement with a spectacle that still baffles astronomers. These stellar remnants, no larger than Earth but packing half the Sun's mass, occasionally wield magnetic fields 1,000,000 times stronger than our planets, twisting their atmospheres into surreal metallic landscapes. Hubble's razor-sharp vision has captured the proof: dead stars with bizarrely geometric cloud formations, where ionized metals like iron and magnesium don't float freely. They're pinned into place like iron filings on a cosmic refrigerator magnet. Take the white dwarf WD0018-266, a case study in celestial strangeness. Spectroscopic analysis revealed its atmosphere isn't evenly mixed. Heavy metals cluster into discrete spots near its magnetic poles, forming glowing metallic archipelagos suspended above the star's surface. These aren't transient features, they persist for decades, locked in place by magnetic fields so intense, they override even the crushing gravity of the white dwarf. Imagine a planet where weather forecasts predict permanent thunderstorms of liquid iron hovering over the north and south poles, never dispersing. That's the reality on these magnetic oddballs. The mechanism behind this metallic imprisonment is both elegant and alien. As a white dwarf cools, heavy elements in its thin atmosphere should sink rapidly due to the star's immense surface gravity. But when strong magnetic fields intervene, charged metal ions spiral along field lines like beads on a wire, funneled toward the magnetic poles where they accumulate. The result, stunning atmospheric dichotomies. Hubble images show some white dwarfs with titanium concentrated in razor-sharp rings, while oxygen dominates the equator, a segregation impossible without magnetism's guiding hand. These metallic spot patterns serve as cosmic X-rays, revealing the hidden structure of a white dwarf's magnetic field. The star read J0317-853, for example, displays 6 distinct metal-rich regions arranged in a perfect hexagon, a dead ringer for the field geometry of a cube magnet, suggesting the white dwarf's field is fundamentally shaped like a toy from a child's science kit. Other stars show more complex geometries. LP40-15 boasts concentric circles of nickel and calcium, resembling a bullseye painted by some celestial archer. What's truly startling is how these magnetic traps rewrite what we know about stellar afterlife. Conventional wisdom said white dwarf atmospheres should homogenize over time, but these metal spots prove certain corpses stay chemically active for billions of years. Recent observations of WD 1822+410 even caught a magnetic field flip in progress, its metallic clouds slowly migrating as the star's poles swapped places, a glacial version of the sun's polarity reversals. The takeaway: even in death, stars can cling to magnetic personalities that defy expectations, turning their final act into a dazzling display of cosmic order sculpted from chaos. What if our universe's magnetism isn't the only possible version, just one variation in an infinite cosmic symphony? Imagine a realm where magnetic forces operate under entirely different rules, where the fine structure constant, that delicate number governing electromagnetism's strength, could be dialed up or down like a cosmic volume knob. In such universes, the very fabric of reality might unravel in ways that make black holes seem tame. Picture a cosmos where magnetism is 10 times stronger. Stars would ignite faster and burn hotter, their lives cut short in furious blue bursts before planets could form. In weaker magnetism realms, galaxies might never spiral at all, just amorphous blobs of gas drifting through eternal darkness. The wildest implications emerge at the quantum level. Our universe's magnetic properties rely on electrons having just the right charge and spin to create stable atoms. Tweak those fundamentals slightly, and you risk atoms that can't bond, or more terrifying, molecules that spontaneously demagnetize. Some theorists suggest that in certain bubble universes, magnetic monopoles might be as common as electrons, creating bizarre materials that attract or repel in only one direction. A compass in such a world wouldn't point north. It might spin endlessly or lock onto the nearest monopole like a moth to flame. Cosmic evolution would take radically different paths. In high magnetism universes, pulsars might outnumber ordinary stars, their intense fields channeling nearly all stellar material into focused jets rather than gentle radiation. Life, if it existed, could rely on magnetic sensing more than vision. Imagine organisms that see by interpreting field lines like Braille across spacetime. At the opposite extreme, low magnetism realities might lack auroras entirely, their atmospheres slowly stripped by unimpeded solar winds, leaving planets as barren as Mars but without even the consolation of polar ice caps. String theory offers an even more mind-bending possibility: brain worlds where magnetism leaks between parallel universes through hidden dimensions. In such scenarios, Earth's occasional magnetic anomalies, places like the South Atlantic anomaly where compasses go haywire, might not be glitches at all. They could be magnetic echoes from a neighboring universe brushing against ours, like fingerprints on a fogged mirror. The Large Hadron Collider has briefly searched for evidence of this, hunting for particles that appear to gain or lose energy mysteriously, potential signs of interactions with unseen magnetic fields beyond our dimensional walls. While purely speculative, these ideas aren't just science fiction, they're stress tests for our understanding of physics. Each hypothetical universe serves as a laboratory where scientists can ask which laws of nature are fundamental and which are cosmic accidents. The fact that even slight magnetic variations appear catastrophic for life as we know it fuels debates about the anthropic principle. The eerie notion that we observe this particular universe simply because its rules allowed us to exist. Whether through multiverses, simulated realities, or undiscovered dimensions, magnetism remains one of nature's most versatile pens, writing different stories across the pages of possibility, each with its own breathtaking consequences. From sculpting stellar nurseries to collimating black hole jets, threading galaxies with invisible filaments, and even imprinting cosmic navigation into the cells of migratory birds, we've witnessed magnetism's 30 faces across the cosmos. It's the silent architect behind spiral galaxies' perfect arms, the cosmic sculptor carving planetary nebulae into glowing hourglasses, and the unseen shield protecting Earth's atmosphere from solar fury. Magnetism choreographs the dance of auroras over Jupiter's poles, whispers quantum secrets to Arctic terns navigating continents, and forges rare elements in supernova shockwaves. It turns neutron stars into celestial lighthouses, stitches the cosmic web with magnetic filaments, and may even hold the blueprint to life's molecular asymmetry. Consider the duality of its power, gentle enough to align interstellar dust grains one by one, yet violent enough to unleash gamma-ray bursts visible across the universe. It threads through protoplanetary disks like a cosmic potter's wheel, shaping solar systems while simultaneously warping spacetime around magnetars into knots of pure energy. From the quantum spin of electrons to the million light-year arcs between galaxy clusters, magnetism operates at every scale, a universal language written in field lines and polarized light. So as the northern lights shimmer or your compass needle steadies north, remember, you're glimpsing the same force that guides cosmic rays, birth stars, and may one day navigate ships between the stars. The universe doesn't just contain magnetic fields, it's fundamentally shaped by them, from the first seconds after the Big Bang to the silent spin of white dwarfs in the galactic graveyard. Now it's your turn. Which magnetic marvel left you awestruck? Was it the idea of primordial fields woven into the universe's fabric, or the chilling precision of black hole jets? Drop your favorite in the comments and stay tuned, because our next cosmic deep dive will unravel an even bigger mystery lurking between the stars. Until then, keep looking up, and remember, every time you flip a compass, you're holding a tool that listens to the universe's hidden magnetic